In the last video, I mentioned that a circle can be defined as a set of points such that the distance from those points to a center point is a constant. I also mentioned that this can be really ambiguous for a definition of a circle when you're thinking of just, the plain old Euclidean circle. After thinking about it over the last week, I realized that I should probably show you why this is the case. And so I'm going to try to do so and then leave you with one of my favorite circles that looks really weird. And basically I'm going to leave it a little bit open-ended. I'm not going to tell you exactly where that circle comes from until next time. So this video is designed so that the first part of it will give you some structure and intuition that will help you approach the problem at the end. But don't worry, I've also included some links to some hints in the cards. Okay, so let's start off with what it means to be a distance function. Distance functions, or metrics, are functions that determine a notion of how far away points are from one another. The metric that you're most likely used to is the Euclidean metric, which looks like this for points x equal to x1, x2, and y equal to y1, y2. This function is a metric because it has the following four properties. 1, it's non-negative, so everything you use in the function will produce some value that is positive or 0. 2, if 2 points are a distance of 0 away from each other, then that means they're equal. 3, metrics are symmetric, so if we measure the distance from x to y and then measure the distance from y to x, they should be the same distances. And 4, metrics are subadditive, which just means that they obey the triangle inequality, which is given as such. If you're not familiar with the triangle inequality, it's kind of like one of the more fundamental tools that is used in analysis. And so if you're not familiar with it, here is a wonderful opportunity to see it. Anyway, now that we have an idea of what it means to be a metric, let's look at some strange circles. The first one, or I guess 3, live in what's called a hedgehog space. Yeah, I know, it's a pretty fun name. For clarity, a K-hedgehog space is kind of like an asterisk without getting into the nitty-gritty details. The only points in the space fall on lines, and there are exactly k of them that extrude from a center point for some cardinal number k. These are also called hedgehogs of spininess k, which also is super fun, so I have been a fan of these things for quite a while. Anyhow, the hedgehog metric is given by the absolute value of the difference between 2 points if they live on the same spine, and the sum of the 2 points if they live on different spines. When we name points on a hedgehog space, we usually specify the spine and then how far along the spine it is. It should be clear in the examples that I will give which spines which points fall on, because I'll be drawing them. But if you were to show this just in plain math text, you would probably specify the spine and how far along on the line you were. So this is an example of a 2 hedgehog space, and the distance between A and B is 2, and the distance between A and C is 7. Now, let's look at a hedgehog with infinitely many spines. Well, I couldn't really draw all of them, so we're going to just use this K hedgehog space 1 and modify it a little bit. So just imagine that there are infinitely many spines coming out of that center point. Now, suppose you have a circle in this hedgehog space. There are 3 different cases. The first case is that the circle has a center at the center of the hedgehog space. Since there are infinitely many spines, this circle will look like a Euclidean circle at face value. But in terms of the hedgehog metric, points that seem close on the circle from a Euclidean point of view are actually very far away in the sense of the hedgehog point of view. In particular, there is a sense of a topological difference between the two. Whereas a Euclidean circle, any 2 points opposite each other on the circle give a diameter. On this type of hedgehog circle, any 2 distinct points on the border of the circle give a diameter of that circle. Second, we can have a similar instance of any 2 distinct points on the boundary of the circle giving a diameter of the circle if they're the only 2 points on the circle. This happens when the center of our circle is far enough away from the center of the hedgehog space, such that the radius is small enough that you can't make it back to the center of the hedgehog space. And then we have the last case, which is arguably the weirdest. First off, the center of our circle is not going to be at the center of the hedgehog space. And second, the radius is going to be large enough that we can reach back to the center of the hedgehog space. In this case, a diameter is not given by any 2 points on the hedgehog circle, which is different from the first two cases. But instead, a diameter is given by the point on the circle that is on the spine that houses the center of the hedgehog circle, which I know is a mouthful, and then any other point on the circle. So, for instance, if you take theta and then any other point that's not theta on this circle, then you have a diameter of that circle. Hopefully by now I've convinced you that circles can be a little bit weirder than you're used to in the Euclidean sense. And this has been mostly a topological change because the fundamental makeup of the space has been altered. You can't move around the circle as you would in a Euclidean space. You have to move back to the center of your space, and then you can move back to a point on the border of the circle in a hedgehog space. However, there are different examples where there's geometric weirdness too. To illustrate this without getting any topological weirdness coming up and interfering with the weirdness that we want, we're going to look at what's called a topologically equivalent metric. And these exist, but for what reasons that they do and why, we're not super interested. So we'll save that for another time. It just means that the different ways of measuring distance can be used to generate the same global space or induce the same topology. An example of one of these topologically equivalent metrics is given by d over d plus 1 for some metric d. Let's consider this ratio metric that is derived from the Euclidean metric. Instead of having non-intuitive topological properties, like with the hedgehog circle where we can't move around the border of the circle freely, we always have to return to the center, these circles have the same topological properties as Euclidean circles do. So if we're given one of these circles that's generated using the ratio metric d over d plus 1, we can move around the border of the circle as we wish. But there's still a little bit of oddity. That is, you cannot have a circle of radius 1. It results in an impossible equality. But you can have a circle of radius 1/2 with this ratio metric that is equivalent to a circle of radius 1 with Euclidean metric. To see why, when we take a circle of radius 1/2, we need a set of x and y such that for every x, d prime sub e of xy is equal to d sub e of xy over 1 plus d sub e of xy, which is equal to 1/2. Manipulating, we get this, and then with some simplifying, we find that d of sub e of xy is equal to 1, which is the same equation for a circle of radius 1 when we take the center as y. So the circles are algebraically the same. There's just a bit of context that is changing between the two scenarios. In this respect, depending on your metric, you can get a circle that is topologically and geometrically different from the image of a circle that you probably have in your brain. But it gets worse, and for me that kind of means more fun. Thus far, I've only shown you circles that result in curves or in points or disjoint unions of the two different objects. However, the following is also a circle, this thing that looks like a filled-in square. Don't get too worried about the boundaries, but note that this is a circle and not a disk. A disk is a circle with its interior, even though this circle would have an area if we took it as a region in the Euclidean plane. It's just defined as a circle in the space in which it lives, that is, in the metric space in which it lives. The riddle, or rather question, is where does this circle come from? One thing though, it lives in the unit square, and so the distance function should be defined on the unit square. I've left some hints in the cards to topics I've covered that might help you think about this problem more. Even though it doesn't directly come up in the videos I've listed, there are ideas there that will help you out. The other thing that you might want to think about is where's the center of the circle, which I forgot to mention like 5 seconds ago. I don't know, it's a fun little problem. Anyhow, that is all I have for you today. If you have an answer at all, you can leave it down in the comments below. If you enjoyed this video, go ahead and give it a thumbs up and subscribe for more mathematics videos. As always, I am Nathan, this is Chalk, and I will see you next time with an answer to that horrible riddle.